Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into distributed cache, the system that enables sub-millisecond reads, massive throughput, and database protection at global scale. We'll cover how companies like Netflix, Twitter, and Uber use distributed caching with consistent hashing, eviction policies, TTL management, and PubSub invalidation to serve billions of requests. Whether you're preparing for a senior engineering interview or building cache infrastructure at scale, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into distributed cache, the backbone of every high-performance system that needs sub-millisecond reads and massive throughput. If you've ever wondered how companies like Netflix, Twitter, or Uber serve billions of requests per second without melting their databases, this is the system that makes it possible. We'll walk through the functional requirements, non-functional requirements, system architecture, end-to-end user journey, core models, low-level design, and the trade-offs that come up in a senior system design interview. We'll cover consistent hashing, cache eviction policies, TTL management, cache-aside versus write-through patterns, replication, and PubSub invalidation. Whether you are preparing for a FANG interview or designing cache infrastructure at scale, let's get into it. Here is the core problem. A large-scale web application serves hundreds of millions of users across the globe. Every page load triggers dozens of back-end calls. User profile lookups, session validation, product catalog queries, recommendation fetches, and feature flag evaluations. If every single one of these hits the primary database, you're looking at tens of millions of queries per second hitting disk-based storage. The database becomes the bottleneck. Latency spikes from 2 milliseconds to 200 milliseconds. Throughput collapses under load. Users experience slow pages, timeouts, and errors. The business loses revenue, engagement drops, and engineering teams scramble to scale vertically, which is expensive and has limits. The solution is a distributed cache layer that sits between your application servers and your database, storing frequently accessed data in memory, responding in microseconds, absorbing read traffic, and protecting the database from being overwhelmed. But designing a distributed cache correctly, with proper sharding, eviction, consistency, failover, and invalidation, is a complex system design problem. Let's walk through the functional requirements. First, the cache must support basic operations. Get to retrieve a value by key, put to store a key-value pair, and delete to remove an entry. Second, it must support TTL time to live, so entries expire automatically after a configurable duration without manual cleanup. Third, it must support multiple eviction policies. LRU for least recently used, LFU for least frequently used, and random eviction, configurable per cache namespace. Fourth, it must support cache invalidation through explicit deletes and through PubSub notifications so that when data changes in the source of truth, all cache nodes holding stale copies are notified. Fifth, it must support atomic operations like compare and swap, increment, and append for use cases like counters, rate limiters, and distributed locks. These 5 capabilities form the core contract of a production distributed cache. Now the non-functional requirements. Latency must be sub-millisecond for reads and low single-digit milliseconds for writes at the 99th percentile. Throughput must scale linearly. Adding more nodes should proportionally increase the number of operations per second the cluster can handle. Availability must be extremely high for 9s or better, because if the cache goes down, the database gets hit with a thundering herd and likely goes down too. The system must be horizontally scalable to hundreds of nodes and terabytes of in-memory data. Data consistency should be tunable. Some use cases tolerate eventual consistency, while others need strong consistency through synchronous replication. Memory efficiency matters because RAM is expensive. The cache must minimize overhead per key and support memory pressure handling gracefully. And finally, the system must handle network partitions and node failures without data loss or prolonged unavailability. Here is the high-level system architecture. On the left, application servers issue cache requests through a client library. The client library implements consistent hashing to determine which cache node owns each key. The cache cluster consists of multiple nodes, each responsible for a range of the hash ring. A coordinator service manages cluster membership, handles node joins and departures, and rebalances the hash ring. For high availability, each key is replicated to one or two successor nodes on the ring. A configuration service like Zookeeper or ext stores the cluster topology and notifies clients of changes. For cache invalidation, a PubSub bus receives change events from the database layer and broadcasts invalidation messages to all nodes holding affected keys. A monitoring service tracks hit rates, latency percentiles, memory usage, and eviction rates across the cluster. The architecture supports both cache-aside, where the application manages reads and writes, and read-through or write-through, where the cache itself talks to the database. The key metrics to memorize cold. Cache hit ratio, the percentage of requests served from cache without hitting the database. A healthy cache should be above 95%. P99 latency, the 99th percentile response time, which should be under 1 millisecond for reads. Throughput, measured in operations per second per node. Modern caches like Redis can handle over 100,000 operations per second on a single node. Eviction rate, how many keys are being evicted per second? A high eviction rate signals the cache is undersized. Memory utilization, the percentage of allocated memory in use. You want to stay between 70 and 90%. Replication lag, how far behind replica nodes are from the primary. Critical for read consistency. Invalidation latency, the time from a database write to the corresponding cache entry being invalidated. These metrics are what the business actually cares about. Let's trace the end-to-end user journey for a read request. A user opens the product page on an e-commerce app. The application server receives the request and needs the product details. It computes the hash of the product key and maps it to a cache node using consistent hashing. The client sends a GET request to that node. The node checks its in-memory hash table. If the key exists and the TTL has not expired, it returns the value immediately. Cache hit, response in under 1 millisecond. If the key is missing or expired, cache miss. The application server falls back to the database, retrieves the data, and issues a put to the cache with the TTL of 5 minutes. The next request for the same product hits the cache. Now let's trace a write. The product price changes. The application updates the database and publishes an invalidation event to the PubSub bus. The bus broadcasts the event. Every cache node holding that key deletes it. The next read triggers a cache miss and fetches the fresh value. This is the cache-aside pattern with PubSub invalidation. The core models and algorithms. Consistent hashing maps keys to nodes on a virtual ring, minimizing key redistribution when nodes join or leave. Virtual nodes ensure even load distribution by assigning multiple positions on the ring to each physical node. The LRU eviction policy uses a doubly linked list combined with a hash map to achieve O1, access, insertion, and eviction. LFU eviction uses a frequency count with a min heap or frequency buckets. TTL management uses a combination of lazy expiration, checking TTL on access, and active expiration, where a background thread periodically scans and removes expired keys. Cache-aside means the application is responsible for populating and invalidating the cache. Write-through means every write goes to both cache and database synchronously. Write behind means writes go to cache first and are asynchronously flushed to the database. The key trade-off is consistency versus performance. Write-through gives stronger consistency but higher write latency, while write behind gives faster writes but risks data loss on crash. Now the low-level design deep dive. Each cache node has an in-memory hash table as the primary data structure, mapping keys to value buffers plus metadata. TTL timestamp, access timestamp, frequency count, and flags. Memory is managed using a slab allocator that pre-allocates fixed-size chunks to reduce fragmentation. The network layer uses an event-driven I/O model epoll on Linux to handle tens of thousands of concurrent connections on a single thread, similar to Redis. The replication protocol is leader-based. Writes go to the primary node, which streams the write-ahead log to replicas asynchronously. For consistent hashing, the client maintains a local copy of the ring configuration, and refreshes it on topology changes via watches on the configuration service. The PubSub invalidation system uses a dedicated channel per key prefix, so nodes only subscribe to relevant invalidation events. Hotkey detection identifies keys with disproportionate access and replicates them to additional nodes, or uses client-side caching to reduce load on the owning node. Key takeaways for your interview. First, always start with the access patterns. Read-heavy workloads benefit from cache-aside with aggressive TTL, while write-heavy workloads need write-through or write-behind depending on consistency requirements. Second, consistent hashing with virtual nodes is the standard sharding strategy. Explain how it minimizes redistribution and handles heterogeneous hardware. Third, eviction policy selection matters. LRU works for most workloads, but LFU is better when access patterns have long-tail popularity distributions. Fourth, cache invalidation is the hardest problem. Discuss PubSub invalidation, TTL as a safety net, and the thundering herd problem with solutions like request coalescing and probabilistic early expiration. Fifth, always discuss failure modes. What happens when a node dies, how replicas promote, what thundering herd looks like, and how you prevent cache stampede. If you can walk through this system with these 5 points, you will signal strong senior-level design thinking. That's it for distributed cache. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on distributed cache. We covered the full picture, from consistent hashing and eviction policies, through cache-aside patterns, TTL management, PubSub invalidation, and the low-level design of cache nodes with slab allocators and event-driven I/O. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.